Physicists have waited over a century for this moment. Since Einstein first dropped his theory in 1916, black holes have remained one of the universe's greatest mysteries. Massive, powerful, yet almost completely invisible. These cosmic giants, millions of times the mass of our Sun, have gone from being nothing more than math on a chalkboard to something we're now beginning to understand up close. And now things just got a whole lot weirder. Michio Kaku recently made headlines with a stunning revelation. We may finally have a glimpse into what lies inside a black hole. This breakthrough could change what we thought we knew about the universe. So buckle up, because we're about to dive deep into the dark heart of space and reveal what's really inside these galactic beasts. Before we unpack Kaku's announcement, let's rewind to how this all started. Most of us have a general idea of what black holes are, but few know the backstory behind how we came to believe they even exist. Back in 1916, Albert Einstein's theory of general relativity predicted the possibility of black holes, a region in space so dense not even light could escape. But it was all theory back then. It wasn't until the 1960s that the first signs of a real black hole appeared. While studying the Cygnus constellation, scientists spotted a strange, ultra-bright blue star emitting X-rays. This star wasn't just hanging there, it was orbiting an invisible companion, something with immense gravitational pull. It wasn't long before they realized those X-rays weren't just hanging out, they were being devoured by this unseen force. That object was eventually named Cygnus X1, and it was the first strong evidence that black holes are not just theoretical, they're real. Located about 6,000 light-years from Earth, Cygnus X1 is roughly 14 times the mass of our Sun. Its gravitational pull is so intense that not even light can escape it, which is why it appears black. And that's what makes black holes both awe-inspiring and terrifying. They don't just pull in matter, they erase it from the observable universe. Get too close and you'll be dragged in forever. No way out, no second chances. That danger has only made scientists more determined to study them. Cygnus X1 was just the beginning. Since then, astronomers have found that there may be over 100 million black holes in our Milky Way galaxy alone. That's right, millions of these silent giants could be lurking nearby, hidden in plain sight. But here's the core of the mystery. What happens inside a black hole? Their gravity is so extreme, anything crossing their boundary, called the event horizon, gets squeezed down to an unimaginably tiny point called a singularity. In simple terms, black holes are like the universe's ultimate vacuum cleaners. But instead of cleaning, they compress everything into a single point of infinite density. And here's the really wild part. If a person were to fall into one, they wouldn't just disappear. They'd be stretched out like spaghetti in a slow, painful process scientists call spaghettification. That's right. The gravity wouldn't just crush you, it would pull you apart, atom by atom. So no, black holes aren't just cool, they're cosmic monsters. Mysterious, deadly, and maybe even holding the keys to understanding where our universe came from, or where it's going. The deeper we go into their secrets, the more questions emerge. But one thing's for sure, this is just the beginning of the story. They're everywhere. So, should we be worried? Even though the nearest known black hole is about 1,500 light-years away, that's still close enough to raise a few eyebrows. In 2021, the scientific world hit a milestone. The first clear image of a black hole was released. It was the mysterious M87 black hole captured over several nights. Piece by piece, image by image, scientists stitched the photos together to create a full visual story of this cosmic monster. What they discovered was mind-blowing. Turns out a black hole isn't just an empty abyss or a gaping void like many of us imagine. It's made up of layers, and things get more intense the deeper you go. Layer 1 is known as the event horizon. Think of it as the ultimate cosmic boundary, the point of no return. Once anything crosses this invisible line, escape becomes impossible. Not even light can get back out. Layer 2 is the photon sphere. This is where light itself gets trapped in orbit around the black hole. Imagine beams of light spinning in circles, unable to break free. It's a swirling chaos of photons doomed to chase their tails forever. Then comes the third layer, the singularity. This is the heart of the black hole, where everything that falls in gets squeezed into an infinitely tiny space. The rules of physics break down here. Time, space, gravity, they stop working the way we understand them. It's a place where reality itself collapses. But here's the kicker. Every black hole is different. While they follow a similar layered structure, their behavior can vary wildly. No two are alike. If this were any other space mystery, we could just aim our telescopes and take a closer look. But black holes don't play that game. We can't see them directly. Instead, scientists study the chaos around them, the way light bends, the gas that heats up, and the radiation they release. And forget about sending a probe like Voyager into one. The moment it crosses the event horizon, it's game over. It would be crushed, stretched, and erased in an instant. Billions of dollars gone in the blink of an eye. So we're stuck trying to understand a three-dimensional phenomenon using two-dimensional observations. To make things even harder, the deeper we try to go, the less our current science can help. The very laws of physics stop working inside a singularity. Black holes don't just challenge our technology, they challenge our entire understanding of reality. That's what makes them so fascinating and so terrifying. That doesn't mean scientists have been sitting idle, far from it. Black holes have sparked a whirlwind of theories, and the deeper we dig, the more fascinating things get. One of the most widely accepted ideas is that black holes are born from dying stars. When a star runs out of fuel, it no longer has the energy to fight against gravity. So gravity wins, and the star begins to cave in on itself. If the star is big enough, this collapse doesn't stop until everything gets squeezed down into a point of unimaginable density known as a singularity. To better understand these cosmic beasts, NASA scientists zoomed in on the core of galaxy M87. What they found was astonishing. A glowing whirlpool of superheated hydrogen gas spinning at 1.2 million miles per hour. At that speed, the gas should have torn itself apart and scattered across space. But it didn't. That meant something incredibly heavy had to be holding it all together at the center, an object weighing 2 to 3 billion times the mass of our sun. The only thing that could possibly explain it? A black hole. But that's not where the surprises end. Back in 1963, New Zealand mathematician Roy Kerr took Einstein's equations and painted a new picture of what a spinning black hole might look like. Instead of collapsing into a single point, Kerr's model suggested that a rotating black hole would form a thin, fiery ring. This ring spins so fast that the centrifugal force stops it from collapsing completely. This swirling region is called the ergosphere, a zone around the black hole where the rules of physics start to bend and twist. But the real mind-bender in Kerr's solution was this. It predicted the presence of something called an Einstein-Rosen bridge, or more popularly, a wormhole. Imagine falling into a black hole, and instead of being crushed, you're funneled through a tunnel in space, exiting somewhere far away, or even in an entirely different universe. Sounds like science fiction, right? But it's actually a theoretical possibility grounded in real physics. To grasp this, picture space-time, the fabric of the universe, as a flat sheet of paper. If you draw two dots and connect them with a line, that's the normal path an object would take. But what if you folded the paper so the dots touched? That's the idea behind a wormhole, a shortcut through the folds of space-time. Now, no one has ever seen a wormhole yet, and they're believed to be highly unstable, collapsing in on themselves almost instantly. But their existence is a real prediction of Einstein's theory of general relativity. If wormholes do exist, it would mean black holes aren't just one-way traps swallowing everything in their path. They could also be gateways, portals leading to distant corners of the universe, or maybe even to other universes entirely. So maybe black holes aren't just the end, they might also be the beginning of something unimaginable. So could we one day travel through space and time using a wormhole? Well, Not quite yet. As exciting as it sounds, the reality is still out of reach, for now. Even if we manage to stabilize a wormhole, it's unlikely we could use it to travel faster than light. According to Einstein's theory of special relativity, the speed of light is nature's ultimate speed limit. Nothing can move through space-time faster than that. Still, the idea of wormholes and black holes acting as tunnels through space or time has captured the imagination of physicists for decades. Imagine jumping across galaxies in seconds or visiting the distant past. If these cosmic shortcuts truly exist and could be harnessed, it would transform everything we know about the universe. One of the most intriguing theories in this field is the Kerr wormhole, named after mathematician Roy Kerr, who applied Einstein's gravity equations to spinning black holes. Unlike traditional black holes that crush everything into a single point, Kerr's spinning black holes might instead form a swirling ring, a possible gateway through space and time. You can picture it like the magical mirror in Alice in Wonderland, a doorway to another world where the usual rules don't apply. The Kerr wormhole could, in theory, link distant parts of the universe, or even different timelines, by pulling you through its spinning ring into an entirely new reality. A place where physics might look completely unfamiliar, yet feel totally normal once you're there. But here's the catch. Even though wormholes make great sci-fi, their real-world existence is still hotly debated. Physicists warn that wormholes, especially the spinning Kerr kind, could be surrounded by intense radiation or chaotic quantum forces that would tear anything apart before it ever got through. Basically, it's not a gentle ride. The problem is that Einstein's equations, brilliant as they are, only explain gravity. They don't account for the unpredictable world of quantum mechanics, where particles behave in wild and mysterious ways. So to truly understand wormholes, or even use them, we'd need something more. A single theory that unites both gravity and quantum physics. This missing piece is often called the theory of everything, the holy grail of physics. And one of the most promising contenders for it is superstring theory. In this theory, everything in the universe, matter, energy, even you, is made up of tiny vibrating strings. Each vibration creates a different kind of particle, like musical notes forming a cosmic melody. The beauty of superstring theory is that it blends Einstein's smooth picture of gravity with the chaotic dance of quantum particles. And here's where it gets really mind-blowing. As these strings ripple through time, they can actually bend space around them, creating black holes, wormholes, and other exotic structures predicted by Einstein's work. That means superstring theory doesn't just explain the universe, it might actually build it. So while wormhole travel isn't possible yet, scientists are inching closer to the keys that could unlock it. One unified theory, one cosmic blueprint, and maybe one day a path through space and time itself. But here's where things get really mind-bending. Superstring theory doesn't just stop at the dimensions we know, length, width, height, and time. It demands something far more complex, a total of 10 dimensions of space-time where these tiny vibrating strings can move and interact. Now, that might sound confusing at first, but oddly enough, it starts to make a kind of deeper sense when you break it down. To imagine this, let's think about a simple pond. Picture fish swimming in the water. They live in a world of just 2 dimensions, forward, backward, and side to side. The idea of up or down doesn't exist for them. But when raindrops fall and ripple the surface, the fish can see the effect of a 3rd dimension, even if they can't experience it directly. We're like those fish. Physicists believe that the extra dimensions predicted by string theory are real but hidden. We can't walk through them or see them directly, but we can detect their influence. The way strings vibrate in those unseen dimensions might actually shape the basic properties of matter, like whether a particle has mass, charge, or spin. In this way, string theory gives us a possible blueprint for everything in the universe, from the tiniest particles to the force of gravity itself. But of course, there's a twist. These extra dimensions are incredibly tiny, so small, in fact, that our current technology can't detect them. Everything we measure in science is limited to our 4 familiar dimensions, which leaves those 6 hidden ones out of reach. So how do scientists even know they're there? One idea is that these extra dimensions are curled up like tiny spirals or loops. Think of a flat sheet of paper rolled so tightly it looks like a single line. An ant crawling on it might not even realize it's walking in circles. In a similar way, the extra dimensions could be all around us, just hidden at a microscopic scale. Another theory says these dimensions were more noticeable right after the Big Bang. In the earliest moments of the universe, all 10 dimensions might have been fully expanded. But as the cosmos grew and cooled, 6 of those dimensions shrank and compacted, leaving the 4 we experience today. If that's true, then ancient traces of those dimensions might still echo through the universe. The math behind all of this is not just complex, it's revolutionary. Superstring theory has pushed mathematicians into completely new territory. But one of its biggest challenges remains unsolved, explaining the behavior of quantum black holes, where gravity and quantum mechanics collide. Still, there's hope. Not long ago, separate teams of physicists made a major breakthrough. They found that string theory can solve the mystery of quantum black holes, but only in a simplified 2-dimensional version of the universe. It's not the full picture, but it's a promising step. Physicist Edward Witten once called superstring theory 21st century physics that fell accidentally into the 20th. And many believe that cracking the black hole puzzle in all 10 dimensions is only a matter of time. Because the equations are there, the framework is ready, it's just waiting for someone to see the rest of the picture. So for now, you can hold off on packing your bags for a trip through a black hole or booking that first-class seat on a time-traveling spaceship. The truth is, when it comes to black holes and wormholes, we're still deep in the theory stage, with way more questions than answers. And even though scientists like Michio Kaku have spent decades trying to make sense of the madness, the road ahead is anything but straightforward. Kaku points out that having countless possible answers isn't a flaw of string theory. It's actually something many powerful theories share. Take Newton's laws, for example. They can explain how a baseball flies or how a planet orbits, but only if you first tell them what situation you're looking at. These starting clues are called initial conditions. Now, here's the twist. For string theory, the starting clue isn't a ball or a rocket. It's the Big Bang itself. Yep, string theory needs to know what the universe looked like in the very first instant it came into being. And that's something we still don't fully understand. There are a couple of ways scientists are tackling this. One approach is to uncover those initial Big Bang conditions through experiments and then plug them into the string theory framework to trace how our universe has evolved since that moment. And believe it or not, physicists have already come up with working models that show this kind of evolution based on some pretty reasonable guesses. The bolder option? Let string theory decide its own starting point. That's a trickier, more uncertain path, but it might one day give us answers we never expected. But here's where Michio Kaku adds another unexpected twist. What if the Big Bang wasn't really a bang at all? Despite the name, the Big Bang wasn't some fiery explosion that shattered the silence of space. It didn't go boom. In fact, the theory doesn't even explain how or why it happened. It just says that it did. To go beyond that, we need something deeper. That's where string theory enters the scene again with a radical idea. What if our universe came from the collision of 2 other universes? Or maybe it branched off from a parent universe, like a cosmic child being born from a mother. In this view, the bridge between universes could be a wormhole, a tunnel connecting 2 realms of space and time, like a straw joining 2 soap bubbles. And here's the wildest idea of all. Maybe we've already found traces of this cosmic umbilical cord. Maybe, just maybe, we're already inside a black hole right now, and we just don't know it. Think about it. We live in 4 dimensions, so we can't see the higher realms beyond us. But what if the black holes we observe out in space are actually gateways to those other dimensions? What if they're not just ends, but beginnings? Crazy? Maybe. Possible? Maybe that too. What do you think? Could we be living in a universe born inside a black hole? Drop your thoughts in the comments below. And if this blew your mind even a little, don't forget to hit that like button and subscribe for more deep dives into the universe's biggest mysteries.